Hi everyone, welcome back to my YouTube channel. Unless you are new, then welcome. So, in my last video, I tell you how you can just simulate. Okay, in my last video of FET simulation, Field Effect Transistor, I just this, input all the parameters that we actually require to simulate FET, and then we design our model, and after that we just select silicon as the material. Now today we have to define the semiconductor. So actually I already brought a semiconductor that I designed before. So for you, what I can do, yeah, so I just brought this semiconductor module because it will take less time. So for you, what I can do, I can add another semiconductor module. So it will help you actually to understand how it's actually working. So add a semiconductor from recent, or you can add semiconductor from. In my last video, I also tell you how you can add semiconductor. So you can add semiconductor from here. Okay. So in semiconductor, what you have to do. So here you can see that we do have a discrete actually module. So I actually prefer to make it group by split dimension. So it's actually group by domain and boundary. So we don't want to talk about boundary now. We want to talk about only domain for uh, actually. Then we'll talk about boundary. Okay. So at first we want to define. We actually have to of our model actually. So for that, here you can see that in semiconductor module, we do have a predefined semiconductor material model and initial values. But we need to define background feed of source end of and drain end of capacitor recombination. All this five thing we need actually. So for that, what we can do, we can click here, and then we can from domain we can select which thing we require, or you can just right click here. We will get all the things from here. So at first we need background p doping. So for that we need a analyte doping module. So just from domain we need, okay, so this is actually the easiest way. So we need analyte doping module. So click here. So we got the analyte doping module. So here you can see that we define it as the background p doping. So actually, if I show you that how it's actually works, so plot the doping profile, then you will get how actually it's working. Okay. Okay. So you can see that we just dope entire model uniformly. So this is the actually the doping concentration. Okay. So here we have to select like doping model. We have to select entire domain. So you can just click here, select all domain. Okay. Then you can select all domain, or you can also do it like sorry, Control A. So sorry, yeah, Control A. You can select Control A. I don't know. I don't know. Okay, so you can just click here. You can and select all the domain easily. Okay, so then what you have to do, we have to select it as a p-type doping. So that's why, and you can just rename it like this. Okay, from this level, you can rename it as background. Sorry, background p-doping, right? Background p-doping, and so this is the accepted doping p type. So you have to select it, and there is another option, do not doping n times so type. So we have to select accepted doping p type, and then the concentration is actually uh, predefined, 10 to the power 17, okay, per centimeter cube. So COMSOL has predefined concentration is 10 to the power 16 per centimeter cube. So we have to make it 10 to the 17 per centimeter cube. So you can take it actually 16. It's okay. So you can see that by plotting token concentration here, you can see that uniformly it's plotted from 10 to the power 17 to 10 to the power 17. Okay. And then we need another source in doping. So for that, we also need analyte doping model. So analyte doping model. So from analyte doping model, we can select the inter domain, and we just can systematically define our source in doping. Okay. So rename it as source in doping. So rename it as source in doping and select the interdomain, and then from distribution you can use user define or box. Okay, so your wish actually. So we are going to select as box. Then it will provide us lots of options. So um, how we can just spread the doping concentration. Okay, so here we need to so this is actually source. So this one actually source. So we have to dope this thing actually, not the entire thing. So that's why you have to choose this one. So we all know the position of this actually source material. So uh, from our okay, from our model we can see that okay, this one is it. Okay, so not this, not, okay, this one actually. Okay, so its position is actually is FET minus H gate. Okay, so let's say take it, and we can uh, so we can put here. So let's say okay, no, not this way. Actually, I'm sorry. Okay, so you can see that if we just select this one, then it's actually spreading like this. But we want only this on or into inside this portion. Okay, so what we have to do? Okay, let's say so it selects 0.7. That's okay actually. So if you don't believe me, okay, let's say just Control C, copy it, and you can paste it here. So you can see that this is actually 0.7. Okay, that's the thing. So okay, and then uh, what we have to do? We have to define the width, then depth and the height. Okay, so we all know the width, depth and height of this thing. So we can take it from this block. Actually, the width is W source. Okay, so let me just so the width is sorry, the width is W source, and the depth is actually DFET and is get right. Height is get okay. Let's get that is fine maybe. So plot it again. Okay, let's see. Okay, it's kind of fine, but we need a more precise thing. Okay, so for that maybe we can take these values actually. They are more precise, I think. So control V 0.6. Okay, let's see 0.8 and 0.1. Okay, 0.8. Okay. 0.8 and 0.1 micrometer. Okay. Okay, so now plot it. Okay, let's see. Okay, It's not that much bad actually. So it was as previous, okay. Uh, but I think, let's see. Okay, this thing is actually showing more precious, but I'm sorry. Doping concentration is N-type and 10 minus 20. Oh, 10 to the 20. Okay. So concentration is also doping concentration is N-type and 1 8 into the power 20% into cube. So now maybe it's, let's see. Yeah, it's kind of perfect, right? So this one actually 0.7 micrometer. Huh? Oh, okay. It's not bad actually. Okay, fine. But I think it must be a bit less. Okay, then it will be okay. So maybe that could be zero point 0.7. Let's see. So everything is fine, right? I'm sorry. Not zero point 0.7 actually. 0.8 is fine. And another thing what I have to do, we have to define the junction depth. Actually, I'm sorry, I forgot it. We have to define the junction depth. Okay, so the junction depth is 0.2, 0.2, and 0.25. Okay, so have to define it. So select it. So 0.2, 0.2, still control V, control V, to 5. Now it's fine, I think. Okay, and for this one, we need 1, 8, and 15% into cube. Okay, okay, it's fine. So plug this on. Now it's maybe okay. Yeah, it's fine now. Okay. So then duplicate this on, duplicate. Okay. So now we need to dope this drain. Okay. So we just dope source. Now we need to dope drain. Okay. So for drain, we have to, so you can see that for drain, the doping concentration is similar, but we have to redefine the position of this. Okay. So as we know, the position of drain, so from, okay, so this one actually maybe for drain. Okay, no. Okay, no, this one. Okay. So position of the drain is actually in x-axis. It is this one. Okay. So we can take it from here and we can paste it. Yeah. So we can check it by plotting. Okay. So here you can see that it's working perfectly. So that's the thing, how we can just dope source and how we can dope drain. So there is another easiest way, but this way is actually more practical, more in practical life. When you fabricate if it is, then it's actually works like this. Okay, that's why we are doing this kind of things. Then we have to, okay, so from domain, we have to take capacitance recombination. So click here and select inter-domain. So, and then for capacitance recombination, it's require electron lifetime and whole lifetime. So actually, uh, so this thing actually silicon the model of silicon is actually available. So you can see that electron model. Okay? So electron lifetime is 10 microsecond and whole lifetime is 10 microsecond. Okay. So if that's all actually for domain and for boundaries. Okay, you can just now open boundary. So for boundary, we do COMSOL does have okay, pretty define these four boundaries, but we need actually metal connection. So basically what we need actually, we need to define this one as a insulator, this one actually metal, so and the background things, all the things we have to define. So for that initially we need to metal connected source. So this is actually metal connected source. So for that from boundary, what you have to do, from boundary you have to take metal contact. Okay, so take metal contact, so select this one. So this is actually our source, right? So metal contact of source. So okay, so and the voltage of the source will be 0. We have to select voltage of the source actually, 0. So rename it as source, and the voltage is 0, is previously defined at 0, so don't worry about it. And then we have to define um, drain. So duplicate this one and deselect this one and select this one and define it as drain. Okay, and then we have to define the drain voltage. So we previously defined drain voltage as DG, VD, right? So in parameters, you can see that where, okay, yeah, this is the drain voltage VD. Okay, let's copy this one and paste this one. Yeah. So this is the drain voltage. Okay, fine. Now we need actually metal contact body. So then duplicate this one again. So this is actually the metal contact body. So we have to select this one. Okay, so deselect this one and select this one. Okay, so this is the metal contact body. So for that, so metal contact body, in metal contact body, we don't need to define the voltage. So it's actually 0. So in source, the voltage is 0. Metal contact body, voltage is 0. So, so this is actually body. Okay. Then again, we need to define insulator. So for insulating gate, we have to take insulating gate from boundary. So okay, in insulating gate, so we have to okay select this insulating gate actually. So this one, this one, this one, this one, and this one. Okay. So this is the insulating gate. Okay. So here we have to define the gate voltage. So in the parameters, we define the gate voltage as VG. So we have to copy this one and we can paste it here. So sorry. We have to paste it here. VG. Okay. Yes. Here we defined previously. So um, homey contact. Okay, this one is actually homey contact. So check it. All the things are homey contact, but this is insulator. So in insulator, you have to define oxide relative permittivity. So I think for this insulator, for actually FET, the oxide relative permittivity is for 4.5 and oxide thickness is 30 nanometer and metal working function is 4.1 volts. Okay, so define all those things. 4.5 is permittivity and 30 nanometer and 4.1 volts. 30 nanometer. Okay, fine. Isn't it okay? Yeah, 30 nanometer, 4.2. So, okay, fine. Everything is fine. Now we have to define the mesh. This is the crucial part. So for mesh, what you can select here or select mesh, and then you can select, um, so I'm sorry. So, mm, okay, we have, okay, from mesh, click right click and then take size. Okay, it will provide you two size. Just delete this one. delete second one. Then from mesh, we have to take, okay, uh, okay, we can take sweep mesh and take size. Size will be custom. Maximum element size is, let's say, 5. Let's do. Okay, so this is not actually good mesh. So what we have to do, we have to select it maximum element size is, let's say, -7. So do this one. Now it's kind of okay, but take more of good mesh. 9. Okay, it will take a bit time. Okay, so if we take the 9, then it will take lots of time actually. So in the case of simulation, it also take lots of time. So I think we are not going to take 3 into 10 to the power -9 because it's for mesh it's taking lots of time. For simulation, it will take again more time. Okay, so we are not going to take that. So just wait until the mesh is fine. Uh, Mesh is done. Okay. Okay. It is taking lots of time. So it is very precious. Precious mesh actually. Okay. 99% is done. Okay, almost there. Almost there. Just wait. Here you can see that number of element is kind of 646806791. Okay, so that's huge actually. Okay, we need 1% more actually. Mm-hmm. We are almost there. Okay. From log, you can see that maximum element qualities. From log, you can see the number of vector element 36, number of edge element 154, number of boundary element is 228, number of elements 132, number of maximum element size is quality is 0.8949. Okay, so that's the thing. And memory, physical memory is it's taking physical memory 1.59 GB, and the virtual memory is taking 1.53 GB. So that's huge actually. And always I told you that when you are simulating console in console, plug in your charger, otherwise your battery will gone. Okay, so maintain the thing. Always plug in your charger. Don't simulate anything in console without plugging your charger. So otherwise your laptop is if you are working in PC then it's okay. But if you are working in laptop then your battery will be gone. Okay, within 3 or 4 months. So you don't want it, right? So uh, always plug in your charger. So you was saying that it's taking lots of time, right? So we we didn't need actually this that much of precise mesh actually. So we have to wait until the mesh is done because if we just uh, cancel this mesh, and then it will take again lots of time. So we don't want that. So that's why I'm waiting till the mesh is done. So sweep mesh is basically is good for uh, semiconductor simulation. Mm, there is other mesh like tetra. I forgot the name of. Uh, okay, I forgot the. Okay, maybe tetrahedral. There is tetrahedral mesh as well, but sweep mesh is better for mm, when you are simulating um, semiconductor thing in 3D actually. Okay, that's why I'm taking sweep mesh. Okay, but you can see that it's taking lots of time. So I'm pausing this video here, and I will back after the mesh is done. Okay. Hi. So you can see that the mesh size is so huge, right? So that's why it was taking lots of time. Okay. See here you can see that this is a huge mesh. Huge means huge mesh. So we cannot simulate this kind of huge mesh actually because it will take lots of time. So we are going to take 10 into 10 plus 7. That's a bit okay. Maybe 1 into 10 to the 7 is okay. Mhm. Yeah, it's fine, completely fine. Though it's pretty high, but I'm going to take 1.5. Okay, I think it's fine. So we can take this kind of measure actually. So it's fine, completely fine because it's not that much. It's not that place actually. So yeah, we are going to take this mesh and then we have to simulate our model. So that's our goal. So for simulating this model, we can get a initial value. So if you just click on right uh, of your mouse, then after clicking studies, then you get this kind of thing, get initial value. So by checking this initial value, it will give you the initial thing that you define in your model. So that's a good thing if you want actually. So yeah, that's a very cool thing. So here you can see that initially this is electron concentration. So you can see that initially the electron concentration is like this. After simulation, it may be be different, but initially this is the thing. So you can see the whole concentration here. So electron concentration is remaining this area and this area, and whole concentration is throughout the mm, things. Okay, and this is the electric potential. Okay, and net doping concentration. So they are actually end up as we know, and they are actually p dop. So we know what we did actually. So electron concentration, whole concentration. Again, it's showing the same thing. Okay. So here are all the things. So we can just check it if it is okay or not. So we check it. It's fine. So all thing completely fine. Then from we define we actually take the stationary condition as we know actually. Okay. Oh. Uh, here I got it. Why it's providing double right? Because we are taking we take two semiconductor modules, so we can delete on semiconductor module. Actually, delete this one. So in your case, maybe you have only one semiconductor module. So in your case, it's complete fine. Fine. Okay. So okay. So I'm going to delete this thing actually. This results. Okay, it will delete all the results. Okay. Then I'm going to search. So I'm going to get the initial value again. So it will provide the initial value this time only one thing. So here you can see that this is the initial value and there is no duplicate initial value. So initially it was providing because uh, we defined two semiconductor. Okay. Then from a stationary study, you have to okay, so in a stationary study, you will get this kind of interface. So inside this kind of interface, you have to just open the study extension. So after opening study extension, you will get this kind of auxiliary sweep. So you have to click on auxiliary sweep, and then from parameter name, so you have to just click on here. Then you will get this parameter name. So so initially you have to click on add, then you will get this kind of thing. So from parameter sweep, we know we define VD, so we click VD, and then you have to define this range. So click here and then click the range. Then you can define 0, 0.01, and 0.02, and it's there. Their unit is volt. You can define it microvolt or volt, whatever. So, but we are working on volt. Okay. And then again, we have to add this thing. So to add this thing, we want to vary the VZ, get voltage. So select VZ, and then for VZ, we want to simulate in such way that we will vary voltage from 0 to 1.4 with respect to 0.2 voltage, and after 1.4 we want to um, vary like 1.4, then 2, then 3, then 4 voltage. Okay, so this way, because um, uh, from 0 point so from 0 voltage to 1.4 voltage, the change of VC is actually very rapid. With sorry, the change of current is very rapid with respect to VC. That's why we are changing. We are taking precise voltage difference. But if we take precise voltage sweep throughout 0 to 4 voltage, then it will take lots of time. So we are not there working like that. So now we can just simulate this thing after that. So select all this thing and then simulate this thing, actually compute. So maybe it will take, I don't know how much time, but it will not take lots of time, I think. So wait until the simulation is done. So almost 5% is done. So you can see that conversation plot. Okay. So this is the error sweeping from this way. So 7% is done. So iteration number 7. So that's not actually looks good. If error should decrease actually. So if it increase, then our simulation will not run actually. So error should decrease. Okay. It's it's actually varying. Okay, okay, let's see. Okay. Okay, again, again, it's increasing. It should decrease actually. Otherwise, we are done actually. It's working, but not a very good way actually. Error is increasing and decreasing, so rapid change. So this kind of rapid change is not low good actually. So we maybe made some mistake in our settings. So that's why maybe it's happening. Okay, wait until the simulation is done. Mm, okay, let's see what happened. This kind of bumping is not actually good. Okay, so okay, so it is showing the error. So yeah, it is showing the error because uh, reach the maximum iteration number. So there is some problem in our model, I think. So that's why it's not showing the final things. Okay. Okay. So we need to find where we just made mistakes. Hmm. Maybe okay, just do this thing. Okay, so it's fine, right? Mhm. Everything is fine, but I don't know why it's showing some problem. It's not actually general physics, it's actually semiconductor physics. Let's see. Okay, fine. Then we can simulate it again, maybe. So basically, if it doesn't showing any specific problem, then in that case, maximum time is actually uh, provide the problem in mesh. So we need to take precise image actually. So again, it's bumping. So I don't think it's actually fixed the problem. So okay, there is another way to solve this kind of problem. So if this actually okay, change increasing, let's should increase, decrease, please. Okay, it's not working. Okay, I'll take another chance actually. There is another way to solve this kind of problem. I'll take that. So let me just pause this video, then I'll tell you how we can solve this problem. Okay. Hi. So I think you are there. So basically, what I told you, the main problem is in mesh actually. So I was selecting wrong mesh. Oh, another thing I noticed during the break actually. So also forget maybe. So make sure these three things actually. So this is actually metal contact source. So the voltage will be zero. Please concentrate in this part actually. This is very crucial part. This uh, physics selecting part and the mesh selecting mesh part. Okay, and then metal contact drain. So you have to select voltage VD as a metal contact drain and metal contact boundary. Maybe here I put a VD actually, so that was actually wrong. So please make sure that you have to select it as zero and then thin insulator gate, and that is actually this thing actually VG. So, and make sure all of this setting is perfect. Okay, then in the mesh, what I did before actually, so that was actually for wrong mesh actually. So, uh, for semiconductor module simulation, when you are doing actually 3D semiconductor simulation, then it is very crucial to select perfect meshes actually. So I'll tell you how we can do this for this model actually. So initially, when okay, so let me take another mesh, then it will be easy to make you understand. So I'm taking another mesh. So that's very fine. So under this mesh, what you have to take? You have to take okay. Okay, from more generators, you have to take free triangular. So don't take free tetrahedral, take free triangular. So take free triangular, then we have to select boundaries. Okay, so select this boundary, this one, all the top boundary. Okay, this one and this one. So all the top boundary you have to select. then build selected. So here you can see that this is perfect. But from size, make sure the mesh is pretty good actually. So otherwise, the thing will not work. So this is perfect for top layer. And then from mesh, click right click, and then you will get a sweep. So select sweep mesh and not remaining. So you have to select domain. So which domain? This domain, this domain, this domain, and this one. So 2, 3, 4, 5, 6. This five domain actually you have to select, and then right click on sweep and then select distribution. So inside distribution, automatically select all the domain. Okay, then here you have to select, okay, predefined. So inside it, you have to select number of elements. So let's say number of element is 10 and element ratio is on, and other things is, you don't need to select anything. So build selected, then you can see that it done this all this mesh actually perfectly. And then duplicate this sweep mesh. Okay, duplicate, and then deselect all the things and select this one. Okay, and inside distribution, what you have to do, you have to select all the things is okay, but this is a very large model, right? So this one was very thin and this one is very thick actually, so that's why we are taking this maybe 20 20 is perfect, and element ratio is zero point 0.1. Okay, and please make sure you have to select this one. Okay, reverse direction. So this is very important for this kind of model. So then select on, right? Okay, build on. So it's perfect. So that was actually the thing you have to select. So inside, I already did this in mesh on. So you can see that initially I take the size. So you can, oh, okay. So what I did actually. So it's not actually general physics. You have to select semiconductor physics for size. Okay. So that's the thing. Okay. So that you if I just make it okay, fine. Mhm. Okay, it's not that it's right actually. Okay, it's fine actually. Okay. So this is the thing what you have to do. Okay, here you can see that for tetrahedral. So I forgot to select this one and this one for. Okay, it's okay, but you can select or not. It's not that much fact actually. So the main fact is actually you have to select this one. Okay, and that is very crucial. So I will show you by selecting mesh one or mesh two as well. Okay, so from semiconductor here you can see that this is there is a mesh part, so you can select mesh on or mesh 2 as well. So I already simulate for mesh on. So let's say now I can simulate for you with mesh 2 that I already just set up in front of you. Okay. And other thing is study extension. Uh, I already discussed this thing before. So I'm not going to discuss this thing again. So then you can just click on compute. So it will run perfectly, I think. So just wait. Uh, okay. So you can see the progress as well. So from this kind of things, you understand that for semiconductor module, mesh is very crucial. So you have to make sure that you select a perfect mesh. So so that your simulation will go through perfectly. Otherwise, it will show a problem. So, um, when I just simulate, I show there is just some issue, right? COMSOL was showing some errors. So I told you that this error is for actually mesh. If you select wrong physics or something wrong inside the materials, then you can get it easily, because when it show errors, then it will show you directly that this thing is wrong. Okay. But for mesh, it shows random error. So it's very tough to understand what's the error actually. So you can see that got the conversation plot. So error is reducing. That is fine actually. Okay. Okay. So if the video is helpful, guys, then you can subscribe our channel, like, comment, share this video with your friends and others. Okay. And if it is not, then you don't need to share it or subscribe our channel. Other thing. Okay. Uh, Again, the road is increasing, but I think it will decrease after that. So don't worry about it. Yeah, you can see that it's decreasing again. Um, so okay, so here you can see that uh, error is decreasing. So it is actually doing the Newton-Raphson method. So if you know that Newton-Raphson method, then you will understand that there is a minimum threshold error, right? So after that, it will told you that this is the result actually. So we need to reach the threshold actually error. So before that if and there is some a number of iterations, so we set in console in there is some inbuilt number of maximum number of newton okay, number of iteration. So basically console done maybe uh, 50 or 20, I forgot. So console basically done 50 to 20 iteration. And if they didn't find better solution within this number of iteration, then they told COMSOL told you that uh, show some error actually. So that is the thing. So if it gets the results within this number of iteration, then it will show you the results. So the good thing is it's reducing. Okay, the error is reducing. So maybe it will take mm, maximum error 10 to the power minus 5 to 10 to the power minus 6. So okay, so I think it's the maximum error actually. So I think next iteration will start for the next voltage. Okay, so yeah, it's taking lots of time. Okay, so you have to wait until the simulation is done. Okay, another thing is okay, I told you before that it will start another iteration. So the for first iteration, the maximum number of maximum error is 8.1 on into 10 power minus 7, right? So that is very minimum error, right? So we can say that the result is very perfect. Okay. So start another iteration. So yeah, decreasing. So that is very good thing for us. So I think it will not take that much time, but only 8% is done. So we need 100%. That's the thing. Okay. So if you can remember what I told you before that we will see the curve of FET actually. after the simulation. So we'll plot the curve of it. Okay. So you have to wait until the simulation is done. Then we can see the curve of the FET. Okay. So it is taking lots of time. So what I can do for you, I can just pause this video here and then I'll show you that, after the simulation is done, I will be back again. Okay. Hi. So finally our simulation is done. So here you can see that it took 1 hour 8 minutes. So it's huge actually. So here you can see that this is electron concentration with respect to different voltage. You can see that by varying gate voltage, it changes in the electron concentration, as well as we can vary the um, okay. So yeah, we can change the gate voltage. Okay. So this is how actually it's working. So whole concentration. Yeah, this is also you can change the voltage and you can check the whole concentration. And this is the electric potential. So you can see that by varying the voltage, this is the electric potential is varying, and, and doping concentration as well as. So it's the same. Okay. So now we need some results. So one D plot group, and then global, and then we need terminal. So we want to plot. Okay, this one. Okay. This is the volt current of terminal one. Okay, we can plot for terminal two as well. This is the current. Okay, this is the current of terminal one and two. Yeah, and we can also plot the current of terminal three. Okay, okay. So here you can see that we plot all the three terminal current. So yeah, so you can plot those things one by one as well. So delete this one and yeah, plot. Okay, then duplicate this one and then for terminal two maybe. Okay, we can plot this one with respect to VG. Okay, there's a thing. And then we can duplicate this one as well. Okay, for terminal three. Okay. So I think you know this one is terminal one. Okay, this is the current of terminal one. So as I think you know what is the terminal one, two, and three. So this is the terminal one. Okay, and this is terminal two. Source is terminal one, drain is terminal two, and this is the body. That is terminal three. Okay, so so here you can see that current of terminal one. Okay, this is the current of terminal one. Okay, and this is the current of terminal two. This is the inverse thing. Okay, uh, with respect to terminal one. So yeah, so you can see that we change the voltage of for different VD, different drain voltage. Okay, so also we can if you want, you can simulate um, VZ with respect to VD. Okay, so you can select VZ here and then you can select VD here. So then you can simulate that. So okay, that's the thing actually. So as I told you before that we will plot this kind of curve. Okay, we get voltage versus the terminal, get voltage versus terminal current. So we plot this kind of graph actually. So Also, we can plot the characteristic curve as well, but um, as you are as you can see that it's taking lots of time for simulation. So that's the thing. Okay, okay. Let me just. So what is the characteristic curve? Need to remember the things. So characteristic curve also drain current versus drain to source voltage. Okay, so this one actually terminal current. Okay, let me check it. Okay, so terminal two is the drain current. Okay, so this is terminal two. This is the drain current actually. Okay, I'm sorry. This is terminal two, and this is the drain current. Okay, drain current with respect to. Okay, if we just plot with respect to VD. So this is uh, drain current with respect to drain to source voltage actually. So that is the thing. Okay. So yeah, you can plot it like this. Mhm. Yeah, that's the thing. So this is the characteristic curve. Okay, if we just plot this way, then it's showing better results actually. So we can plot it micro ampere maybe. Yeah. So then you can see that the thing. Okay. So this is the base way actually. So you can see that this is increasing, and after that it's actually get constant actually. That's the thing. Okay. Okay. So now this is how we can just simulate yeah, field effect transistor. Okay. So if you want more video like this, you can comment and you can ask for more video. And also, if you want that I make further video on FET or MOSFET, then you can comment. Then I can prepare another video for MOSFET or Field Transistor. So to see more characteristics, so it is taking lots of time. That's why I'm not simulating another simulation actually. So if we just simulate by changing PG and PD, then we can get the characteristics are properly. Okay, as we've seen in past video. So I'm not going to do that actually right now because it's taking lots of time. So as you can see that this first simulation takes 1 hour 8 minutes. So that is huge actually. So yeah, that's the actually um okay fine. Okay, so guys, that's a wrap. Uh, see you.